Hi, everyone. Welcome to my talk. This is on the age of our universe. Just a reminder, my name is Dr. Christina Sweeney Hillesheim, and this is the next talk in my science and religion series. So you're welcome to go to one of the first talks or one of the earlier talks if you would like, but you are more than welcome to just jump in here at this talk as well. So, the age of the universe. So, science specifically, the Big Bang, has the age of the universe to be 13.8 billion years. However, if we look at religion, specifically Christianity, the Bible says that the time from the beginning, the Big Bang, to humanity is only 6 days. So, which is right? And how can both be correct or are neither correct? Now, we already kind of talked about the age of the universe and the Big Bang in one of my earlier talks, so you're welcome to go back and check that one out. But now we want to kind of talk about this apparent discrepancy between 13.8 billion years and 6 days. How do we kind of make that work, or does it not work? And here's a fun little graphic if kind of like some religious humor. So, how do we measuring the age of our universe? So, some people initially started to use carbon 14. This was used kind of since the 1940s, and it was a standard method for dating, specifically using for fossils. However, it only worked for fairly young fossils, about 30,000 years, which is not very much if we're thinking of billions of years. And the way that you had to validate this measurement was it was determined based on the amount of radioactive carbon in the atmosphere. However, that number, that amount must be constant from the beginning of the Big Bang until now. And how is it produced? So it's produced by cosmic rays that are smashing into nitrogen atoms near the top of Earth's atmosphere. And that's how we get carbon 14. However, over time and with new advances in scientific technology, there's been evidence showing that this cosmic radiation has not been absolutely constant kind of throughout the age of the universe, out the eras. So it's good for fossil dating and kind of shorter time where we know that the variation in the carbon radiation didn't change a lot. But in these longer time spans, it's not a very good measurement. So then how can we then measure it? So another measurement is uranium thorium. You can see them here, number 90, number 92 on the periodic table. And so these are really good for measurements because they're independent of cosmic radiation. So they're not going to have that same effect of that variation of the radiation throughout the time scale. However, the aging has kind of shown to match pretty well with carbon 14 dating regarding fossils and other things that have been tested. So it gives approximately the same ages, and they often differ by 10 to 20%. And you might think, well, 10 to 20%, that's a lot, that's pretty high number, like 20%. But actually, in the big, scheme picture of things, it's really not that big of a difference. So, for example, if we're measuring the age of a 30,000-year-old bone, you may get the age to be 24,000 instead of 30,000. You might think 6,000 years, that's a lot of years. But if we're thinking in the comparison of billions of years, then it's kind of only like a little bit of a drop in the bucket. And so it'll be in the same time period, same eras. However, in comparison to the biblical worldview, the Bible would say that the oldest thing would be about 6,000 years old. So then, how do we rectify this if we have fossil bones that are 30,000 years? And this isn't even thinking about before animals were on the planet and before all that, going all the way back to the Big Bang. And we get 6,000 years for the age compared to the Bible. And I'll talk about where I get these 6,000 from in a second as well. So how do we want to think about measuring time? So we need to think about how do we describe time? So how is time described from a scientific perspective and how is time described from a biblical perspective? So let's first talk about it from a biblical perspective. So time is described in the Bible may not really be the same as time today. So we're kind of thinking about it as what we're used to with our time, 24-hour days, 60 seconds in a minute, etc. But we can see that in the Bible, time is described a little differently. So here's an example. Psalms 94 says, 1,000 years in your sight are like a day that has just gone by, or like a watch in the night. So here it's describing 1,000 years being almost equivalent to just a day. So is it possible that the 6 days of Genesis could include the 13 and some change billion years of the universe? Could there be some relationship with those two, like it says here in Psalms 90? So let's look at this a little bit more. So I just want to have a caveat here. If you have looked at anything studying, Genesis or the age of the universe, maybe you've looked at kind of different theories as to how to explain the 6 days of Genesis. There are some theories that say that each day were really epochs, lasting millions or even billions of years. So they're saying like there's ages within the day. And so that's one theory, but that's not what I'm saying. So I'm not saying that each day was really millions or billions of years old. Okay. Because in the ancient commentaries, it states definitively that these were 6 days of Genesis and they were considered 24 hours each. So the 6 days of kind of like a work week. The 6 days of Genesis actually did not contain the billion years of the cosmos, even while the days remained 24-hour days. So I don't want you to kind of think about it from that perspective that I'm saying, oh, well, they're saying it's 24, but it's really millions and billions of years old. It's not both and in that sense. Okay. So you might be saying, well, then what will you say? And I will answer that question. So let's first look at, from the biblical perspective, how do they kind of talk about the 6 days before Adam and Eve? So in the fall of 2020, the biblical calendar reached the year 5,781. And this is calculated by adding the ages of the generations of humankind as they're listed in the Bible and all the rulers after. So you can start with Adam and Eve. They have all the genealogies, and there's been several people that have gone through and done all the math for us. So the biblical calendar is about 5,781, and you can adjust that based on what year that you're watching this video. But what marks the beginning of this biblical calendar? So logically, you might think, well, the calendar should start with the creation of the world. So when everything starts, that's when the calendar should start. But really what's actually, so it would be the generations of Adam. So if we're thinking about doing the math, so we'd say, here's Adam, take all the genealogies, add up all that, and then plus the 6 days of Genesis. However, the starting date is actually the creation of humankind in Genesis 1:27. That's where the calendar starts. It doesn't actually start with the creation of the universe. So ancient scholars actually excluded the 6 days of Genesis from the biblical calendar. And so let me explain to you why. So if you were to take the Bible, read the account of Genesis, and then read other segments of the Bible, you'll see that the description of time in the Bible is actually described in two different ways. It's kind of divided up into two categories. So you have the first 6 days, and then you have all the time thereafter. So the way that the first 6 days in the book of Genesis is described, it's described as blocks of events. This happened, this happened, this happened, and then a day passed. There's no really intimate relation between the events and the passage of time. It's not this happened, it took this long, it lasted this long. There's no correlation saying, oh, it took, the land and waters were separated. It took 12 hours to do that. There's no correlation between the events and the passages of time. It just says, for example, the land and water separated, plant life appeared, and there was evening and there was morning the third day. There's no hint given for the time each of these major events took place. However, after those 6 days and the rest of the Bible, the events now become kind of the cause of the flow of time. And time is actually tied to earthly events. So Adam and Eve live 130 years. They're the parents of Seth. So now we have an event and we have specific times kind of attached to it. So we can kind of see and say, okay, this happened, this is how long it took. So the way time is described is different in the second division of time in the Bible. So those 6 days are not included in the calendar. Um, because also in the Bible, kind of what we were talking about earlier as well, because within those 6 24-hour days are all the secrets and ages of the universe. And this idea is also similar to the Psalm verse I mentioned, based on two other biblical verses. So Genesis 2:4 says, "These are the generations of the heavens and the earth when they were created in the day that the eternal God made earth and heavens." So generations and day. This is the book of the generations of Adam and the day that God created Adam. So generations and day. So, like before, when we looked at the Psalm passage and we saw thousands of years as to one day's passed, here we're seeing generations are juxtaposed to days. So, within those first 6 24-hour days, time seems to be described very differently. So let's kind of change gears a little bit. We understand that the Bible is describing time in a way that is not, it's a little hard for us to grasp. Generations in a day, thousands of years in a day, that's kind of a little abstract. So let's just move to science and think about, how does science help us understand time? How do we define time? How do we understand it? So in 1915, Einstein published the law of relativity. At the time, it was just a theory, but now it's been accepted as a law. And it states that the rate at which time passes is not the same in all places. So time is based on location, and time is going to change based on gravity and or velocity. So if we have changes in gravity or if we have changes in velocity, that's going to change our perception of time. But we need huge changes. So we need huge changes in gravity, huge changes in velocity for us to kind of see these measurable changes in flow of time. So the flow of time at a location with really high gravity or high velocity is actually going to be slower than at another location with lower gravity or velocity. So if one place has high gravity, one place has low gravity, they're going to experience time differently. The higher gravity, time will be slower. The lower gravity, time will be faster. And this difference in these two locations and this time passage is known as time dilation. So in case you're kind of like, I'm not really following you, Christina, can you give me kind of an example? So I'll give you an example. So here's kind of a picture. So imagine a planet with a massive gravity. Okay, so really, really big planet compared to our little small planet here in the picture. And this planet has a gravity that's 350,000 times relative to Earth's gravity. So it's a lot stronger. Okay, so a lot stronger gravity, higher gravity, that means it's going to have a slower time. So if it's 350,000 times stronger gravity, it's going to be 350 times slower relative to the Earth's time. So our imaginary planet compared to Earth. So how do we kind of think through that? Okay, so the time on Earth compared to the time on the planet. So while on Earth, 2 years will pass, while on the imaginary planet, only 3 minutes would pass. Okay, so your perception of time is going to be affected by where you're at in relationship to your gravity and in comparison to other places. So let me just give you an example. So say I'm an 11-year-old girl, I'm on Earth, and I decide to fly to this imaginary planet. Say I get there really quick. It's like, boom, I'm on this imaginary planet. So we don't have the time change, like loss of time for traveling. So now I'm on the imaginary planet for 3 minutes. So I'm only on this planet for 3 minutes. When I return back to Earth, 2 years would have passed. Because remember I said, while on Earth, 2 years will pass, and on the imaginary planet, only 3 minutes. So I go to the imaginary planet for 3 minutes, and when I come back, all my friends are now 13, and I'm 11 plus 3 minutes. So let's kind of, and there's a few movies that have actually really helped with this. So Interstellar is one that kind of help you kind of imagine this time dilation, because it is a little bit tricky to kind of wrap your head around. And so what's actually happening is there's one set of events. There's the 3 minutes that happen on the imaginary planet and the 2 years that happen on Earth. Both are occurring in exactly the same time. Both the 3 minutes and the 2 years is correct time. It's all relative. That's where we get the law of relativity, because time is going to be relative based on where you're located. And it's going to feel the same when you're on the massive planets, the imaginary planets. The 3 minutes isn't like flying by. It feels like 3 normal minutes for you. And if you're on Earth, it feels like 2 normal years for you. But as you transition from one to the other, that's where we see the effect of this gravity and this slowing of time. So each planet and each star has its own gravity and its own velocity. So each one is going to have its own age, its own kind of clock. So how it views time and how time passes. So on Earth, we know we have our own Earth clock, 1 year. But let's say, for example, the sun. So Earth would be equal to 1 year, where the time on the sun would be 1 year minus 67 seconds. So if we want to think about 1 year happens on Earth, but on the sun, it was 1 year minus 67 seconds. But how do we actually figure this out? How do we know what the time is on the sun? No one's going to the sun and looking at their watch and measuring it. So we can actually measure this from the sunbeams that we receive from the sun. So we can actually calculate this. So as the light is coming from the sun and traveling to us, it's getting stretched. And I'll just explain this a little bit more on the next slide as well. So they're going to get stretched. And as it's stretched, it actually is stretched longer by 2.12 parts in a million relative to Earth-generated light. So we can compare the light that comes from the sun compared to light generated on Earth, and we can see the comparison is that the sunlight is stretched by 2.12 parts in a million. So let's try to think what that means. So what it means is for every million Earth seconds, the sun loses 2.2 seconds relative to our clocks on Earth. So that's 67 sun seconds per year. So that's how we get that it is 1 year minus the 67 seconds on the sun. So it's interesting that you can say, okay, there's 1 year on Earth, but on the sun, it's 1 year minus 67 seconds on the sun. So you might say, okay, well, we've got a lot of different locations. We have Earth, we have the sun, we have stars, we have lots of different, we have other planets, we have other galaxies. So there's got to be a place in the universe where the clock could tick down so slowly that 14 billion Earth years would pass, while that clock in that location would only be 6 24-hour days. So you might be thinking, oh, is that what we're talking about? You might think that, but remember that individual locations did not exist in the 6 days of Genesis, because nothing existed at the very beginning. Then we're talking about the creation of things. So with this law of relativity, we have to compare from one location to the next. Earth's location to something else. But at that time, there wasn't other planets and stars. So then what are we going to compare it to, since we can't compare it to a physical location, mass? Okay, so let's just go back to the Bible and let's think a little bit more about the facts that we talked about when it comes to the Bible. So there's 3 facts about the description of time that we find in the Bible. Like I said, the biblical calendar is divided into 2 sections. First, the 6 days of Genesis, and then all the time thereafter. Now, the time in the biblical calendar after Adam must have been earth based time because then Adam, everybody that is being described, is located on earth. And so we would measure that time based on earth based time. We can we can confirm this by looking at radioactive dates of archaeological discoveries. It actually matches the same times of when things were set to happen in the biblical calendar. So, for example, the Battle of Jericho, if you go through and you look, like I said, here's Adam, you go through all the generations and you map out when the Battle of Jericho should have happened. We actually have archaeological findings that we can radioactively date and find that it matches with the biblical calendar. So we can see that all the time after Adam matches with our earth-based understanding, with that biblical calendar. But those 6 days before, there's no way that they would have been earth-based time because for the first 2 days, there was no earth. So if we look at Genesis 1-2, so how are we going to measure those 6 days? So we've got the second part, but how do we measure the first 6 days when we're talking about the whole length of time? So let's go back to understanding a little bit more about how do we measure light and how do we think about this cosmic clock. So if we're trying to measure it, we can say, okay, well, if there were no planets, there were no stars, then we're just kind of in space. So how are we going to measure the relativity of space compared to Earth, especially when Earth wasn't there at the time, but comparing it to now? So let's just review a little bit about light. So light is both a particle and a wave, and we want to look at the wave-like aspect of this. Like I said, we were able to figure out the sun's relationship to Earth, the sun's clock based on Earth's clock, because we understand how the light from the sun is behaving. So this wave aspect of light allows us to measure it over long distances. We know that all light travels at the same speed, at 3 times 10 to the 8 meters per second. However, that wavelength varies, and the wavelength is the difference between the top and the top of like our waves. So the top of one wave to the top of the next wave is our wavelength. And so how far apart it's going to be is going to be different. You might have a longer wavelength and you might have a shorter wavelength, depending on the distance between the tops. Now, we have a lot of different types of light. So we have radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, gamma, etc. And it's all based on that wavelength. But we only can see a very small part of it. So even though there's light happening, we can only see that is in the visible light range, which is only 400 to 700 nanometers. So most of the light we don't get to see with just our eyes. We have to use different equipment to be able to measure. So the shorter the wavelength, if the peaks are really close together, then that means it's a higher frequency, meaning there's going to be more waves coming. Because they're closer together, you'll see more of the waves. And the higher the frequency, the higher the energy. Now, in this case, velocity is remaining constant. So it's not speeding up or slowing down. We're just separating the distance between the peaks with the frequency. So this is important because we are trying to measure these rays that are coming from, for example, previously from the sun. But how are we going to measure that if there's no sun, no stars, no earth? So during the first 6 days of Genesis, time is not from a specific place because there's no place. Time is just the entire universe as it's evolving. And so this is a little more explained in my lecture on the Big Bang, so you're welcome to go back and watch that one. But I will kind of do a little bit of a summary. So just after the Big Bang, the universe begins to expand. And the relative passage of time is varied only very slightly. It's expanding and time is pretty consistent at that point. but the proper local time was not established, meaning, Earth time wasn't established, sun time wasn't established because there was no stars or planets with their own gravities and velocities. So we only had universe time, cosmic time. Now, as the universe expands, we do get stars, we get planets, and they will then have their own cosmic clocks, their own clocks, Earth clock, sun clock, etc. So we need to measure the time before these stars and planets. So how can we do this? So because the Big Bang released so much energy, we're going to have some of that energy left over, some residual energy. And this is called the cosmic microwave background radiation. And the picture that you can see on this slide is actually the picture of this radiation around Earth. And so it fills the entire universe. So this radiation is throughout the universe, and this is the radiation that is going to allow us to actually determine what is the cosmic clock. So because this radiation is going to have its own wavelength and frequency, we can measure it. So you might think, well, it's not light, but it is because it's just not in the visible light spectrum. So we can't see it, but we can still measure it. And so we can treat this just like we could treat the sunbeams coming from the sun. So we can take the radiation and we can measure the radiation's relationship to Earth. So this cosmic microwave background radiation, the frequency is going to form the basis of our cosmic clock. Okay? And so that will help us to understand what was the clock of the Bible and those first 6 days of Genesis. So at the Big Bang, I just want to clarify a few things. There are 3 aspects that affect radiation frequency because we need to know what's the wavelength, what's the frequency of this radiation. So there's 3 things: velocity, gravity, and then the stretching of space as the universe expands. So as the universe expands, this increases the wavelength. So as it stretches, then it's going to stretch those peaks of our waves further away. And if it stretches the peaks of the waves, we won't see those peaks as often, which means it also lowers the frequency. If it lowers the frequency, it's going to lower the ticking of the cosmic clock, slow it down. So for example, as the universe doubled in size, the distance between our wave crests doubled as the wave was stretched, and thus the time would be passing at half its original rate. And so this is how that stretching of space is going to affect our time measurements. So at the Big Bang, our entire universe was in a small little speck. And then it started to expand and expand and is still expanding. And so now the edge of the universe is billions of light years away. And just to give you an idea of what we're talking about from a distance standpoint, 1 light year is 10 million kilometers. So as the universe was expanding, it's also cooling. And so for us to have matter, to have stars, to have planets, we need to have a lot of energy. So this is also the famous equation E equals mc squared. So for us to have mass, matter, we need energy. So as the universe was expanding, we have a lot of energy, but it's starting to cool. And so as it's cooling, we're going to get below that minimum threshold temperature. And below that temperature is when matter cannot now be formed anymore. In a sense, no more protons and neutrons can be formed. So there's that point where what we have is what we have. Okay. And so once we hit that, which happened very quickly. So after the Big Bang, we hit that temperature measurement, and then we're still expanding, but we have what we have. Creation of the protons, neutrons, stars, elements, matter, all of that is complete. So then we can actually determine what the temperature and the frequency of that radiation is when we hit that threshold temperature. So when the threshold temperature was reached, we know the temperature and the frequency of the energy in the universe at that time. And so that energy actually had a frequency a million times greater than the radiation of today's cosmic background radiation. Okay, so we know what the energy level then compared to our cosmic background radiation. So what that means is the difference was a million. So the radiation had been stretched a million fold. So, and remember, if we're stretching the radiation, we're stretching the wavelength, we're stretching the frequency. What that does is the longer the wavelength, the lower the frequency, the lower our clock. So that stretching has slowed the frequency of our cosmic clock by a million. So now our time difference is by a million. So the age of the universe is based on Earth's clock, and we need to adjust it to be the cosmic clock. So this is how we're doing our comparison. So before we said maybe Earth and the sun was our example. Now we're doing Earth and space, like the universe, our cosmic clock. Okay? And so that difference, that adjustment from Earth to the sun was 67 seconds a year, but from Earth to the cosmic clock is a million. So now we need to do that calculation. So what does this mean? So the cosmic clock records the passage of 1 minute, while on Earth it experiences a million minutes. So that's our comparison. We have that million stretching. So if you actually take 13.82 billion years and divide that by a million, and actually reduces those 13.82 billion years to 6 days, which is just remarkable. So if the universe had been any other size, temperature, or mass, this relationship would not exist. The mass and the energy of the expansion of the universe is actually fine-tuned. And I have another lecture on the fine-tuning, how precise different aspects and different laws of our universe are and constants. You can also go watch that lecture if you would like. But the mass and the energy of how our universe is expanding is fine-tuned to 10 to the 120th. So very precise. And so for it to be that precise, that's how we're able to have the age of the universe, that 13.82 billion years that has been scientifically confirmed, and how that can be changed or compared when we're talking about Earth time versus cosmic clock time to 6 24-hour days. And so this is how we can understand the idea of generations in a day, of thousands of years in the passing of a night. And so when it says that, we're not talking about, ages passing, where what we're talking about is thinking about how is time. And time is relative based on your location. And so cosmic clock versus Earth clock. So we were looking at that first question of, can you have 13.82 billion years as the age of the universe? And can the 6 days of creation of Genesis both be correct? And the answer is yes. So in my next talk, I'll actually be breaking down those 6 days of Genesis. So what actually is happening in each of those 6 days from the Bible, and then what is actually happening in our scientific record. What is happening? How long does it take? And does that match if we do these conversions with that cosmic clock? If we convert from the cosmic clock to Earth, does it match what we see in the scientific record? So here are my references for this talk. Here's just a few of them. And I just thank you so much for watching my talk. And I hope you enjoy this one. And I hope you watch more to come.